Alright, hello and welcome to the Midterm 1 review. I'm recording this separately because I don't know if we'll have enough class time to get through everything that I would like to review, so you get a video. You're welcome. So, yeah, I'm going to write a bunch of code, I'll give you the code, and yeah, let's get right into it. I can't review every little thing, of course, and that's what class time is. Ask me questions, please, please, please. But here is a lot of stuff. Hopefully you're going to get a good bang for your buck. Okay? So the first thing that I want to talk about is data representation, because we need to know exactly how everything is being encoded in memory when we're making a program, right? So at least on ARM32, as far as it is concerned, ints and pointers and registers are all holding 32 bits of data. Okay, that's 4 bytes total, so every int takes up 4 bytes. So for example, if you had an array of ints with 3 in them, and maybe you knew that the first int, like there's your array of ints, and you knew that the first element of the array lived at address 100, it takes up 4 bytes total, so that you know that the next thing is going to live at 104. The next thing after that is going to live at 108. Okay, that is the idea. And same if you had like an array of pointers, which is think argv, right? Char star argv bracket bracket. It's an array of C strings, which are just pointers to characters, so it's really an array of pointers, okay, to the start of a C string. And so that's what you were doing in that lab. Yeah, you were dealing with pointers, and you have to advance 4 bytes to get to the next 32-bit pointer. Okay, so yeah, that's those. And then strings are made up of a bunch of characters, right? Every string is just a bunch of characters, and each character in ASCII land is encoded with a single byte. So like, here's hello, and every character is exactly 1 byte long. Okay, so you'll have to use like load B and store B if you want to get a single byte out of memory. So for example, if this lived at address 200, the next character, the E, would live at address 201. After that, it'd be 202. If only I could write numbers properly. Okay, that's the idea. And then 203, 204. That is, a string is really just an array of characters, but C strings are special strings. They always end in a null terminator character. Okay, that's the \0, or really it's the number 0 encoded as a single byte. Okay, that's what that is. And that just marks the end of a C string so that like printf knows when to stop looking through the string and printing out characters. Okay? And in your data section, when you're defining strings, usually if you're using any C library stuff, you're gonna call it ASCII-Z. This would be ASCII-Z hello, this whole thing. Right? Because this will put that 0 byte at the end, the null terminator character. That's what we want. Where if you were to do just ASCII hello, it would not put the null terminator character. That would give you just this bit. Maybe if I could do that. I hope that makes sense. Okay, but ASCII-Z gives you that null terminator character also, which is very useful if you're going to use printf. Okay, so that's data representation in a nutshell. Doubles are 8 bytes long. I had a slide somewhere that talked about all that stuff, and I'm sure the books talk about that as well. But this is the most relevant stuff, I think, from your labs and things. So that is data representation. Let's move on to registers now, because we're going to use those a lot when we're writing our assembly code, right? So in ARM32 land, you get 16 registers total, and some of them have special names. Those high up ones have special names. The others, they're just R0 through R12, okay? What I want you to remember, especially when you're making function calls, is that R0 through R3 and also R12 are called your scratch registers, okay? They get clobbered. You might actually be clobbering them yourself if you're making a function call and those functions take parameters. Either you're clobbering these things or the function itself is allowed to overwrite them and do scratch work with them, okay? So if you need these values after a function call, after you do like a BL printf, then you better save these away in one of those safe registers like R4 through R11 or somewhere on the stack, okay? because you are not guaranteed that these values are what they were after a function call. They are scratch registers. They're allowed to be overwritten. Okay, R4 through R11, as far as the, I guess the ABI, the Application Binary Interface, says is that everybody's supposed to protect R4 through R11. So if a function that you call uses these registers, they better save what was originally there and restore that thing before they return. And so that's why you see a lot of push, at least in my code, just so that we don't have to think about it, push all of them. Push R4 through R11, and then we also like to push RLR, because we usually make function calls. So that's saving all of those original values on the stack so that we can pop them later, okay? And get them to be how they used to be, okay? Those are our preserved registers. That is the idea. So yeah, those are the normal registers. The rest of them have special meaning. SP is always a pointer. It's the address of the top thing on the stack. The last thing that was placed onto the stack, SP holds a pointer to that place, okay? Go back to the slides to review that if you need to. I'll give you an example of the stack a bit later in this lecture, or in this review session. And then we have LR. LR is always set by a BL. That's a function call. BL sets LR to be the address of the next assembly instruction so that you know where to go back to, okay? And so that's why we end up popping into PC, because we want to put where we need to go to into PC, and PC holds the address of the current instruction, the one that you want to execute, okay? I put current in quotes because most of the time it holds the address of like 2 instructions ahead, but when you want to go somewhere, when you want to jump to a certain line of code, you just set PC and it'll go straight there, okay? It's a weird little process, but it works. So PC is short for program counter. That is just your address of your current instruction. That's, or at least how I want you to think about it, okay? Those are your registers. Please yell at me in class if you have any questions about this stuff, because now we're ready to get to real code, okay? So let's go through simple hello world in a bunch of different ways so you can get a feel for the differences, okay? So let's talk about how we do it in C first. That's probably the most familiar. So hello underscore C dot C, because every C file has .c as its extension. If we want to print stuff, we want to include standard io.h, okay? And then the rest is how we know and love. It's a main function with return 0, and if we want to print something, it's not cout in C, it's printf, right? So we'll say hello world, new line, okay? So that is C in a nutshell, and I noticed that what I should have done is made myself 2 screens, so let me go and do that now. So back to the file, and then I can compile it down here. Yay. And so that's hello world, simple C program. All right, next, how about a version of hello world in assembly with start? So not a main function, the most primitive, a start label, and we'll use the write syscall because we're not going to use the C standard library. We're going to compile with AS and LD, okay? We're going to assemble, that is. So here is a list of syscalls, and it looks like I need to go to the ARM version, so let's sort by ARM. And write, the thing that we would like to do first, is syscall number 4, and you can click on it to see more information about write. It takes 3 things, 3 arguments. A file descriptor, which is a number that represents a file that you want to write to, and we're going to use standard out for the standard output on the terminal. So the number 1, that's what it is, and then we give it the characters that we want to print, so the string, and the address of it, of course, and then the size in bytes that we would like to print, the number of characters, that is. Okay, that's the size in bytes of your string. Okie dokie. And so those things, these parameters to the write syscall, they go in R0 onwards. So R0, R1, and R2, and the syscall number goes in R7. Okay, so you can have at most 6, I guess, parameters to syscall, and that's plenty. And then to actually make the syscall happen, we say SWI0. SWI stands for software interrupt. It just says, okay, operating system, I have made a, I'm ready to make a syscall. I've got everything ready. I've got R7 with the proper values, and then all the parameters that you were expecting for that particular syscall number 4. I'm good to go. Go and do the thing. Okay? So that's the idea. So let's do that in assembly with just start. Okay, so let's do hello start .s, and so if we want to start, we gotta say that it's global so that the assembler can see it, and then we'll just say, okay, here's where it begins, and it's underscore start. And so what we do first is set up the write syscall, and then once we're done writing what we want, we need to exit the program with a 0 return code as usual, because nothing went wrong. And yeah, that is the idea. We want to print a string, and so we should make space for that string somewhere. The data section is a great place for that. That's where global data gets stored. Technically, because the string we want to print is a constant string, we can also put it with the code, but this is fine. Okay? So I'll call it, I don't know, stir, because I am not very original. And because this is the write syscall, it doesn't care about a null terminator string. We just got to tell it how many characters to print. So I'll use ASCII instead of ASCII-Z. Okay? And a new line, and this appears to be 14 characters. Okay? So let's remember that. So it looks like we got to move into R7. The number of the syscall we want to make, which is 4, it's the number of the write syscall. And then R0 is the number 1, because we want to print, we want to write to the standard output. 1, that's the terminal. It's number 1. And then R1, it should actually be the address of the string, so it needs to be LDR R1 equals stir. That gets the address of the string, puts it in R1. And then move into R2, the size of that string, which if I remember correctly, it was 14. Okay? And so that sets up the syscall, and this actually makes the syscall. Okay? The rest of these just set up the syscall. Okay? And so that'll write, and it will continue with the code, and it will try and go all the way to the data section if we let it. We have to stop the program with a syscall. That's how programs end on Linux. So we have to make a call to the exit syscall. Okay? So let's look at it. The exit syscall is syscall number 1 because it's important. And what it takes is the status code that we want to exit with. Okay? So it takes 1 parameter, and it's syscall number 1. So we got to do very similar things. So this. So exit is syscall number 1. We want to exit with a return code of 0. The first parameter goes in R0 for a syscall, so we'll put 0 there. Okay, and then make the syscall. I hope that makes some sense. Set up the syscall and perform the syscall. Okay, so that is the idea. And then to compile, to assemble, there is no compilation necessary because we're already in assembly. You use AS. Okay, so you say AS hello start .s, and then you can give it an output file, hello start.o, and then to make an executable file, you link it. You say ld hello start with any optional libraries, and we're not using any, so just link it by itself into an executable file called hello start, and if I run it, it prints hello world, a new line, and exits. Okay, so that is that program. And then finally, let's do it. Oops, I was just looking at all these things to steal from. Oops, I went into the wrong one. Back to that one. Let's close off that one then. Then, let's do it in assembly with a main function this time, and a call to printf. Okay, that's the last way we can do this. So, I can maybe try and take a lot of this. Hello main.s. So, I can copy most of this, oops, paste. But it's really going to be global main, right? And then it's like type main function with a percent sign, and then some other stuff that I cannot always remember, so I'm just going to cheat and go up here and take a look at what it needs to be. But there's a style, right? It looks like it's func main. That's right. Okay, so I'll steal those. Bam. And everything else looks right. Cool. So here we are in main, and We don't need start anymore. We don't need write anymore. We don't need exit anymore. We just need to do stuff, okay? So in main, what needs to happen? Well, we better print a string, right? So maybe I should keep what we had, stir. This is almost right, but because we're going to print in C, we want to use the C library. It needs a C string, so you got to use ASCII Z there. And so we're going to set up the call to printf. I'm going to say printf, and then the stir. And so the idea is we're going to make a call to printf. This actually makes the call with BL. And before that, we got to put stir in its right spot. And remember that our arguments go in R0 through R4, or sorry, R0 through R3, and that's the first 4 arguments. The rest get pushed onto the stack in opposite order, remember that? And so we only have one argument to printf, it's the string, and so let's put it in R0. And by putting a string, I mean put the address of it, because that's what a C string is, the address of the first character. And so that's there, we call printf, and it goes on its merry way. But remember, making a call to a function clobbers R0 through R4, and also, it's definitely going to clobber LR, because every BL call sets LR. So if we want to return from main, we better have saved somewhere at least LR. We're not using any of the other savable registers, and so we don't need to save them, but we better save LR, because we're going to need it later. BL is going to clobber LR, because it needs to save the address of the next instruction that I'm going to write right here, right? The move R0, 0, and then we can pop into PC. Okay? So when we call BL printf, it sets LR to be the address of this instruction, because that's where it needs to come back to. So we better have saved the one that we needed to come back to up here. Okay? That's the idea. So that's saved on the stack now, and this returns 0. Because to return from a function, you just need to go to wherever the LR was saying, because it's saving the place we need to return to. So there's some start label somewhere, and that's where we need to go. So that's popping into PC, wherever, whatever we were saving on the stack, and that was LR. Okay, so the old value of LR gets placed into PC, and that jumps us to where we need to go. Okay, and by putting in R0 a value, that's where you put return things. So R0 is where you put anything you want to return from a function before you actually return. And so we're putting 0 there so that we return 0 from main. Okay? So in theory, that's correct. And we can use GCC to compile now because we have a main function. We need to do that so that includes the right library as well, the C library. And there it goes, hello main. And so it makes the call to printf, and then we make sure to save where we need to return to. Then we set up our return. We put into R0 the value that we want to return from main, and then we pop whatever was on the top of the stack into PC, and that was our LR value, which is the place we need to return to. Okay, so that's the nice trick way of returning from a function. Okay, and that's what we needed to print in our data section, that string. So that is printing hello world in 3 different ways. You're welcome. There's other assembly stuff that we can do. I have maybe a combined example that we can use because it's just, the idea is we're going to make a bunch of labels if we ever want to branch / loop. Comparisons are very important. There's always, it's always B and then some stuff, right? So B, BEQ, BNE, BLT for less than, BLE for less than or equal to, all that stuff. Remember that. Okay, so let me give you just a fancy program that does this. Okay, so let's sum all the numbers from 1 to 10 and use the sum as the exit code of the program. All right, we could use that as a main function. We could do that as just a syscall. So we could do it like hello start maybe, and copy all this, because we're just going to exit with a certain thing, so maybe we don't need to touch anything else. That sounds good to me. So like arithmetic.s, we don't need to write, we just need to exit with a special return code in R0. Okay, so let's put into R0 what we want to exit with. The return code that we want to exit with. So what do we want to do? Let's sum the numbers from 1 to 10 and use the sum as the exit code. So let's sum 1 to 10 into R0. Okay. That's the idea. So here's how we do it. Let's just use R0 as our accumulator. So we'll move 0 in there initially, and then we want to have like a counter, right? So let's use R1 for like our I variable for our counter. Start it at 0, make sure it's always less than 10. Okay, it's like we want to do for R1 equals 0, R1 is less than 10, etc. That's the idea, right? Let's make this look like a real for loop. R1 plus plus. That's what we would like to do. And so we'll use R1 as our iteration variable. Start it at 0. Okay, so that's like the first line of the for loop. And then we want to compare. We want to see if we want to keep adding into R1, which is our iteration variable, if we want to keep adding that into R0. So we'll say compare R1 with 10, because we're trying to do this right now. We're trying to compare R1 with 10 and see if it's less than. Okay, so it's a two-step process in assembly. First you have to do the comparison, which is secretly doing a subtraction, and then we have to ask it, okay, is it what we wanted? Okay, so branch something. Usually I like to branch for loops with the opposite condition. We'll just like branch to the done label. So I'll put like a done label down here. That will work. And we want to branch. We want to stop the loop if the opposite of this is true. So we want to continue if R1 is less than 10, but we want to stop if it ever hits 10, if it's ever greater than or equal to 10. Okay? So we could either use BEQ because of the way we're doing it, stop if we're equal to 10, if that comparison was equal, or stop if we're greater than or equal to. That's the true opposite of the less than, so I'll use this one. Okay? No real difference though. So first is the comparison, and then branch based on the comparison. Okay? It's always a two-step process, unless it's a BAL. So branch if greater than or equal to. That's what BGE means. So branch if R1 was greater than or equal to 10 to the done label. Okay, and we can make as many labels as we want, call them whatever we want. So that's what we're doing there. Otherwise, continue with the body. So what we want to do here is say R0 equals R0 plus R1, and then we also want to do R1 plus plus. Okay, so let's do both of those. So add into R0 itself plus R1, and then add into R1 itself and the number 1. Okay, and so that will just keep on doing the loop. Eventually it'll go to done, but actually it's not going to ever come back up yet, is it? We want to continue, we want to keep looping, right? We want to, from here, after this is done, we want to go right back up to this, to the top of the loop, which would be the comparison, right? So that's like where the loop begins. So we got a branch there, okay? Continue the loop again, okay? With a BAL, or just a B. BAL stands for branch always. That's the one time you don't need a comparison. Just always go to the loop, no matter what. Okay? Unconditional jump. So this goes straight back to the loop, and we can continue this as much as we want, as long as we don't get to this, and branch greater than or equal to the done. That brings us there, and that stops us. Okay? So by the time we're done, we have the right answer in R0, and that's what we need for the exit syscall. So R0 already has the proper value, the one we want to exit with, and then we will just say that we want to do the exit syscall and make it happen. Okay? R0 has the proper value. I hope that makes sense. We don't need any data, so we're not printing anything, not saving anything. But that is, I think, what I want. So let's do AS arithmetic -o arithmetic.o, LD arithmetic.o, arithmetic, and moment of truth. I think the answer is like, what, 55 or something? Let's see the exit code. Oh, it's 45. Darn. Oh, shoot. Yeah, I was doing it wrong. We got to start, this is how we should be iterating. 1 and then less than or equal to 10. Huh. Or, like, strictly less than 11, right? That will have R1 range between 1 and 10. Silly me. So let's change that to that, and that to that. That'll fix it. LD, oops, try again, run, then echo. Okay, that's the correct answer. So yeah, it's a loop, and it's comparing and branching, and the reason it's a loop is because it's branching back upwards. If you want to do a comparison, a simple comparison, you'll just branch always downwards, okay? No real difference. The devil is in the comparison and the branching, okay? That's the idea. So that is some random arithmetic stuff, and then the last simple example that I want to show you is like an example of the read syscall, because that's very similar to write, but slightly different, right? So here's read, it's syscall number 3, and what it takes is all the same stuff as write. The file that you want to read from this time, the buffer, the place in memory that you want to write to, all the bytes that you read from the user, or wherever the file is that you're reading from, and then also the count, the number of bytes that you're trying to get, the number of things that you want to read. Okay, so for example, I think I got last time like a initials. That's a good amount of things to read. Read exactly 3 characters, but really 4 because we need the new line. So let's do that. Copy read.s. So what needs to happen with a read syscall is, let's set up the return 0 and everything. And then let's do the read syscall here. And I think I don't want these comments, right? Oh no, that's what I wanted. I wrote those for that file. Okay, actually I think I want to copy in the hello start, because that's mostly the same, isn't it? Well, if only I can get back to where I was. There we go. So we want to make the read syscall, which is syscall number 3, and we want to get the initials from the user. So get 3 chars from the user with the read syscall. Remember, that's really 4 because we have to say that we want the new line as well. Okay, we got to eat that up. So here's what needs to happen. R0 is the file that you want to read from, which in our case now is standard input, the keyboard on the terminal. So R0 needs to be 0 this time. That's the number of that file. And then in R1 goes the place in memory that we want to write to when we get that stuff from the user. So in the data section, let's make stir again, and it can be ASCII, whatever, just be 4 X's or something. Okay? This memory will get overwritten by the read syscall, because it's writing to here whatever it reads. And we got to say how many characters that we want to get. If we're getting a bunch of initials from the user, we have to, like that'll be 3 characters. We also want that new line, so we have to say 4 total, okay? And yeah, that'll get it and put it into stir, whatever we get, okay? That's the idea. And I guess the simplest possible thing that we could do is write it back out. So let's just go back and write out exactly what we got from the user. Yay. So that would be here and here. Hello. Goes. And so we'll write out what we just read. So it's going to be 4 bytes, because it's 4 characters that we're putting in here. And it'll also have the new line character built into it, because we'll get the 3 characters from the user, they'll press enter, and then we'll also eat up that new line, which is nice. So yeah, just read into the string, and then write out that string that we just read into. Okay? That's the idea. Let's do AS. This is read.s, read.o, LD, read.o, into read, and then read. So I'm going to get 3 things. my initials are LHN, enter, and it got them, it put them in memory, and it printed them back out. Okay, so that's the read sys call in a nutshell. Yeah, the last thing in assembly that I want to show you is how to write and call functions, okay? So, yeah, let's make an assembly main function and have it call a +1 function, okay? So we're just going to be like int main, essentially, in assembly, of course, and we'll have it call +1, be like printf, an integer, and that will be the call to the +1 function of, like, I don't know, 42. So it should give back 43 and print 43, right? So we're going to write this function here. And then we should print it out as well with printf or something. Okay? So that's the idea. That's what I would like to do. And I guess I'm going to do this video in 2 parts because I'm getting hungry now. And so I'm going to go eat something, and I will be back to record the rest. All right. I am back. Let us continue. So yeah, let's make this function. Or let's make these 2 functions, main and then also +1. Okay. Might as well make them in one file. It's probably the easiest that way. So what's a good name to call this? +1.s? I want to make a new file called that. There we go. And let's steal somebody's main function. So I guess this one. And alright, where were we? So there's a main function for us, at least. And what else do we need here? So I'm going to do the most generic main function with save as many registers as we can. And we'll pop them as well at the end. Because who knows what we're going to do inside of it. So printf, yeah, it looks like we're going to have to call +1, which we're eventually going to make, right? So call +1 of 42, so we can then print it. Okay, so the way that you call a function, right, is you put into R0 your first parameter, and then after that R1, R2, R3, and on the stack. But we only have 1, so let's put into R0 42, the parameter that we want to call +1 with, and then we'll make the call, bl +1. And so now, because +1 returns something, it's going to be like int +1 of int x or something. It's going to return whatever its result is, which will be in our case 43. So now, and that will be put in R0, because R0 is where return values go. Okay, so now we want to print that value, print that number. And so we're going to use printf to work like this. We'll say printf %d for an integer and then a new line. That'll be our string, and then we'll also give it like R0 or something. That's how we want to do this. So let's put the string that we need to use for printf down here. And so yeah, because in R0 is where the first parameter of a function call goes, we kind of just clobbered the value that we wanted to print. So that value itself, needs to go as the second parameter of printf, which means it needs to go in R1. Does that make sense? So move R into R1, R0. So this is the result. It goes into R1 because that needs to be the first parameter, or the second, either the 1th parameter, if you consider this the 0th parameter, or the second parameter of printf. Okay, so that goes in R1, and then in R0, of course, goes the first parameter. So that's the string that we want to use to do the printing. Okay, and so those are the correct calls to printf and to +1. All right, and so now all we have to do is make the +1 function. And the easiest way to do it is just make a new one. If you have 2 functions in the same file, you have to say end func so that the assembler doesn't get confused between them. But now I can just do the same thing for +1. Okay, so I'll replace all this main with +1. Still a function, still global, all that stuff. So this is like int +1 int x or something. That's how you would declare it in C. And so here's how we're going to make it. So again, we have push and pop things. and pop into PC, because that's where we return to, and now we can do the work. And so our parameter, or our argument, is in R0, and our return value also goes in R0. Okay, so essentially we have a +1 function. We need to take our parameter, our argument, and add 1 to it, and then return it. Okay, the returning happens here in the pop, where we replace PC with our old LR value. So all we really need to do is increment our argument by 1. Isn't that nice? So yeah, that's about it. Because the return value goes also in R0, well, just take your parameter, add 1 to it, and now it's suddenly our return value, and return from the function. Okay? And so the data is only being used by the main function, but that should do it. Okay, so we have, we call +1 with 42, we're going to get 43 back in R0, because that's where return values go. And then down here, we take that value, put it into R1, because we're going to call printf, and it needs to be the second parameter, that thing that we want to print, because the first parameter is always our format string. And then we make the call to printf, okay? And finally return 0 from main itself. So that, in a nutshell, is a complicated assembly program that prints 43, okay? So let's do this. Let's compile gcc +1.s -o +1, and let's see what if I missed. Line 21, it's not happy. Oh, I forgot a comma there. That'll do it. Oops. There it goes. Now it's happy. And bam, does it print 43. Okay? This is a very involved program, I hope. It's useful, though, for studying purposes. So yeah, I think I explained it as much as I can. So yeah, take a look at this and make sure you understand it. That is +1. There's the function, and we're calling it inside of the main function. Okay? And oops, sorry for the weird edit. I just now realized that I forgot to use a local variable on the stack to do some work. That was something that I wanted to show you, but I just glossed right through that. Excuse me. So let me go back and let's change how we did our +1. Instead of adding to R0 the number 1, let us do stack stuff instead. Okay, so let's make room on the stack to do our intermediate work. And so what we need to do is take something away from SP. Okay, remember that SP stores a pointer. That register holds a pointer to the top piece of the stack. And the stack grows downward as well. Okay? Towards the lower addresses in memory. So if we want to make space on the stack, we need to subtract from SP. Okay, so to make one new 32-bit sized thing, one new 4-byte sized thing to hold an int on the stack, I need to subtract 4 from SP. Okay. Okay, so that's what I'll do. I'll say sub SP 4, and so that'll take 4 away from SP, and now if I were to dereference SP wherever it's pointing to now, that's new space for me to hold a local variable. Okay? So if I were to use like the brackets SP, will get me access to that new place that I made for myself. Okay, those 4 bytes where I can hold a register's value. All right, so our argument went in R0, but let's do our intermediate work on the stack. So let's put our argument into SP, into our local variable. That is sitting at SP right now. Okay, so we will store into SP that value. Okay, R0, please go into SP, just like that. Okay, does that make sense? And so we could do work just like that. We could get the value back if we wanted to. It's a bit of a contrived example. I am well aware of that. But yeah, we could do our work just like this. If we wanted to get it off into some register or something like that, we could, this is just all pretend, but if we had a local variable sitting on the stack, if we wanted to do work with it, we'd have to bring it back into a register, right? So we'd have to do something like load into like R1 or something from SP. We can do our work there, do something like that. Okay, add 1 to R1 because that's where the value of the variable is now, and then we'll store it back just in case we need R1 for something else now. Well, it'll be tucked away safely, our return value, on the stack. So we'd store into SP the value that's sitting in R1. Yeah, hopefully that's making a little bit of sense. And so if we want to return something, we want to return the thing that's on the top of our stack, we need to get it off of the stack into R0, right? So again, a lot of unnecessary loads in the stores, I know, but this is just getting us some practice, right? So load off of the stack, go to that place that the stack is pointing to, get the first thing on top at that address, put it in R0, and that's what we're going to return with. But remember to also clean up the stack. The stack needs to look exactly as it was before we started doing stuff to it. Okay, so remember to clean yourself up when you're done with all your local variables when you're about to return, right? So otherwise, this pop call would be getting random things. It wouldn't be getting the right values, right? They'd be a bit offset, and that would be wrong. So to get rid of that space we made for ourselves on the stack, we just need to say that the stack is a bit higher up in memory now, okay? To take away those 4 bytes that we subtracted. So add into SP the number 4. And it looks like I forgot the number sign up here too. Okay, so that, in a nutshell, is using the stack for things. We're making room, and so we wanted 4 bytes of room, so we can just keep using SP because that's the top of the stack. That's the address of the thing that's at the top, and we were using that. Okay, hopefully that makes a little bit of sense. Please yell at me if it does not. Let me just show you this working. We'll do gcc +1.s. See if we made any silly mistakes, but no, we still get 43. Awesome. So I'm going to try and edit this back into the video as well as I can, but that is the entire example that I wanted to give. Okay, so let us now move on. Fun stuff. So the last few slides have nothing to do with code, at least, which is nice. So let us talk about those, and that will be the review. Let's make sure I'm actually recording. Yes, good. All right, so the next stuff is the von Neumann architecture and ISAs, and also memory stuff. So yeah, just remember this kind of diagram. You have, in the von Neumann architecture, there is the CPU, which consists of 2 separate parts, we say. There is the processing unit with registers, all those places that you could store things temporarily, and then there's also the ALU, which, remember, it looks like a pair of pants. Now that you know about it, I think I drew it backwards. Whee, there it is. That is an ALU, very small, and that does all the work, all the thinking, add 2 registers, save in a third, things like that. That's the processing unit, which is aptly named. And then we have the control unit, which is figuring out what to do, okay? So the PC is what's going on here, and then other things that, like the flags and stuff. So this is saving memory, like where do we need to go? Where are we looking inside of our memory, okay? Where is the instruction that we're currently loading? What do we need to do to complete that instruction's execution? Maybe we need to take from memory and put into a register. The control unit is orchestrating all of that, okay? And then these are all connected via buses. Buses are just a bunch of wires that allow the CPU to transfer stuff to and from places. And yeah, like if you want to load something from memory, the CPU is going to send out on the address bus which address it wants to load. The control bus is going to say, oh, I want it to be a load and not a store, and then the data bus is going to take the information from the memory unit and place it into maybe a register or something, okay? And all this stuff happens just as easily for input and output units. They're all connected, okay? Controlled by somebody. All right, so that is the picture that I want you to have in your mind. Not too bad, just a bunch of interconnectedness, and you know more of these terms now than when I first showed you this picture, so it should come a bit easier. So yeah, that's the von Neumann architecture, and you can build as fancy of a processor as you want based on these. We've talked about RISC and CISC, reduced instruction set computing, complicated or complex instruction set computing. When you see RISC, think ARM. When you see CISC, think x86 Intel stuff. Just simpler instructions in ARM. Remember, there was no modulus instruction, for example. x86 gets a bit fancier. That's the main difference. And yeah, it's just a matter of personal choice. They're both coexisting in the world right now, in your phone or in your desktop computer. And yeah, an ISA stands for instruction set architecture. It's just the way that you're encoding things. You say like, okay, the add R0, R0, 1 instruction, we're going to encode that as this string of 32 bits. Okay, that's all. That's essentially what an ISA means. It's just the language that the CPU speaks. It's the binary encoding of all your instructions. It's just the rules you have to follow. Okay, so obviously there are different rules for different processors. You can't run ARM compiled code on an x86 machine unless you're emulating it. Okay, so that's the idea there. And remember your memory stuff. If I make this big for a second, you have maybe I should just zoom in down here. You have very fast things like registers at the very top. It's very quick to get stuff from them. And then at the very bottom you have like the internet or your hard drives, things like that. It takes a while to get information there. And so we would like to, for locality purposes, if you remember that term, we'd like to keep things closer to the CPU if we can, in these smaller places like the registers, the caches, the main memory. And that's why we load everything. Like if you want to run a program that's saved on your hard drive, you load it into main memory before you start executing. Okay? Because it's much faster to get at the next instruction. Things like that. Okay? So these three are the primary memory, very fast, close to the CPU, and secondary storage are things farther away. Okay, so yeah, that is essentially all I need to say there. Just remember the order and things like that. Yeah, the last two slides are a bit more of just plug and chug kind of work that you know how to do now. So let's do base conversion. So I have two examples, one to convert to decimal, which is the easy way, and then from decimal, which is the harder way. Okay, so let's do this first one. Let's convert this number to decimal, and remember that all you have to do is use that exponential expansion, that base expansion thing. So this is the rightmost digit, so it's a 0 times 2 to the 0. It's the 2 to the 0's place, plus a 1 times the 2 to the 1's place, plus a 1 times the 2 to the 2's place. And then I'll skip the other zeros, and this is 0, 1, 2, 3, 4, 5. 1 times 2 to the 5. Okay, and so if you add them all together, that is 2, 4, 8, 16, 32 plus 4 plus 2. And so that's 32 plus 6, which appears to be 40, in theory. So, yeah, that is the number I have for you. Okay, so that's 40 in decimal. Okay, hopefully that makes sense. Sorry if I made a mistake, but that, at least you know the process. Okay, and then the other way involves a bunch of repeated remainders and then also integer division. So if we want to go from this decimal number to, let's say, hexadecimal, that's probably the easiest place to go to first. You will take the number and start modding by the base you want to go to. Okay, so mod 16, 35 mod 16, let's figure out whatever that is. Uh, 35 mod 16, that is apparently 3. Okay, so that's your rightmost hex digit. It is a 3. Okay, that's how we work. And then we want to shift away the 3 in hex from 35. So we say 35 integer divide by 16. And I think it's going to go in twice, right? 32. So with some remainder left over, but we drop the remainder, just do integer division like C++ would. 35 integer divide by 16, just 2. And then we do this with the 2. 2 mod 16, use the same process. That's just 2. And then 2 integer divide by 16, that is 0, and so we're done. And so every time we took a modulus, we get a digit in reverse order. So it looks like 35 in decimal, in hexadecimal, is 2, 3. Okay? And we can confirm that by taking this expansion. It's 3 times 16 to the 0, which is 1, plus 2 times 16 to the 1. Okay, so it's 32 plus 3, which is 35. Yeah, that works out. And then to go from here to binary, it's very easy, right? You just pretend that each of these digits is 4 bits long, because that's how many a hex digit takes up. So you just convert 3 to a 4-bit number with some leading zeros if necessary. So that's 3 in binary, but every hex digit takes up 4 bits, sorry. And so that would be the 3, and then this would be the 2. Okay, so this is the binary form. So if you want to like squish them together, remove the leading zeros, it would be 1, 0, 0, 0, 1, 1. Okay, base 2. And so these would be your 2 answers there. And yeah, an exercise for you would be to try to convert that to octal. Okay, what would be your plan? How would you do it? Okay, think about the fastest way. So that's base conversion in a nutshell. Always remember it's mod and divide by the base you're trying to convert to. Okay, and you always do decimal arithmetic, because that's what we know how to do as humans. Okay, so you start with a decimal number. All right. Yeah, the final thing that I want to talk about in this review is our logic gates. Remember what they look like, what they do. The AND gate performs the AND operation, which has a ton of different symbols. This is probably the one I prefer the most, but in C++, you have your bitwise AND and your logical AND with the ampersands. And then OR is any of these symbols, and NOT is any of these symbols, right? So yeah, let us have a little example here where we make a circuit for all this. And I do encourage you to pause the video and try it yourself. So yeah, let's just make it happen. If we have 3 inputs, we need 3 wires coming in. So X, Y, and Z. Let's see if I can make it this small, we'll find out. It looks like I'm eventually going to need not Y, so let's invert Y with an inverter or a NOT gate. Okay, and so out here now is going to be not Y coming out. I like to draw it with this kind of symbol, not Y. It's just easier for me. That's what I'm used to. So then we're going to take X and we're going to AND it with that, so we need an AND gate. Whee, which looks like a little bullet from Mario. And so that would hold X and not Y. Okay. And then I need to work on this guy over here, so Z and not X. So it looks like we need not X. So let's take a bit of X, jump over there, not that, and so that gives me not X. And we want to AND that with Z. The order doesn't really matter, so we could just put Z on the bottom there. And yeah, that gives us these 2 sides over here coming out of both of those AND gates. And then the final thing is to OR them together. Okay, let's see here. Actually, I think I should have drawn the parentheses like this. It's a bit arbitrary otherwise, but yeah, AND binds tighter than OR usually. So let's pretend that that is true. So then we have an OR gate at the very end to bring them all together, and so this would be your output over here. Okay, and so that's how I would draw this circuit, and you can go and you can look at it and try and figure out like what's the output when X is 1, Y is 0, and Z is 1. So if you allow it, let me just put like a 1 here in green, a 0 here, and a 1 here, and we'll go through all these gates. Okay, so coming out of the NOT gate here for Y is going to be a 1. Coming out of the NOT gate here for X, because X was 1, is going to be a 0. And so anything with a 0, we don't even care what Z is, that's automatically a 0 coming out of this AND gate. And this X is a 1, and we have a 1 coming in on both sides, so coming out of that AND gate is a 1. And so it looks like when we OR those together, we get 1 or 0, which is just a 1, okay? Because OR takes true whenever it can. Okay, so I think that is the answer, unless I made a silly mistake, but hopefully you can read it and do this kind of thing. Okay, so that is logic gates. So that's everything that I made in terms of slides. Obviously there was a lot of lecture content that I shrunk down, so it's not everything, but I hope it was a lot and a good amount of things that you were wondering about. Please ask me in class if there's anything else that you're worried about, and I'd be glad to give you an example or to like build on top of whatever I did here today. So yeah, I think that's all I have for you. Please yell at me in class or online somehow, and I will make sure that you are ready. So yeah, that's all I have for you, and I will see you later.